Welcome to this explainer. We're diving right into grade 7 robotics today. Specifically, we're zoning in on a really crucial foundation. Unit 1, Lesson 2, Basic Movements and Guided Notes. We're going to unpack the key concepts, some real-worked examples, and the transfer tasks that actually teach these machines how to interact with the world literally from scratch. So whether you're a student, an educator, or just kind of fascinated by how things work, you're in the right spot to see how junior high students tackle the wild challenge of robotics. Let's get into it.
Okay, so here's the big question we're answering. How do we get these machines to actually do what we want, reliably? I mean, it sounds simple enough, right? Just tell the robot to move. But as any grade 7 student finds out super quickly, robots don't speak English, and they definitely don't make assumptions. They literally only do exactly what you tell them to do.
Here is our roadmap for today. 1. Unit 1, Basic Robot Movements. 2. Unit 2, Sensing the Environment. 3. Unit 3, Program Control Flow. And 4, Debugging and Predicting Behavior. Section 1. Unit 1, Basic Robot Movements. The Muscles and Skeleton.
Diving right into the Unit 1, Lesson 2 guided notes. The very first thing we do is establish some absolute non-negotiable safety rules and physical setup protocols. We really need to ensure everything runs smoothly, right? So before a robot even flexes its muscles, students figure out how to safely handle the hardware. Then they jump straight into the core application task, executing basic movement commands. This is where the rubber literally meets the road. But there is a massive conceptual hurdle to clear first. The big realization for students here is that a robot's muscles, its motors, are completely blind. They need incredibly precise movement commands to do anything reliably. Imagine, trying to walk across your classroom with your eyes squeezed shut and earplugs in. That is your robot's motor. If you tell that totally unaware motor to just move forward, well, it doesn't know what forward means, how fast to go or when to stop, unless you give it those exact parameters. And this is where the real learning happens, this core iterative loop. You write the basic movement, run it, test how the motor behaves, and revise based on what just happened. In the lesson's guided worked examples, a 7th grader might be tasked with programming the robot to move, say, exactly 10 inches. They write the instruction, hit run, and eagerly watch, only to see it completely miss the mark and smash into a desk. So they pull out a ruler, test the motor behavior, and instantly start debugging. It's this constant loop of testing and revising that builds a student's confidence in controlling those initial blind motors.
Section 2, Unit 2, Sensing the Environment, Giving the Robot Senses.
So once students have those basic movements from Lesson 2 down, the ultimate transfer task is applying them to sensors. How can our machine use sensor data to respond to its environment? We're shifting from just pushing rigid, blind commands out to the robot to having the robot pull information in from its surroundings. Suddenly, those basic movements become reactive.
Just compare simple, rigid commands to actual environmental detection. A rigid command dictates moving forward exactly 5 steps. Well, if someone drops a box in the way on step 3, the robot just crashes right into it, helplessly spinning its wheels trying to finish those last 2 steps. But a sensor-based behavior tells the robot to move forward until it senses a wall. Now, the machine is actively checking its environment and stopping intelligently. It's a total game changer.
To pull this off, students learn to identify what different sensors actually do, read their input data, and, this is huge, explain their physical limitations. That last point is absolutely critical. Sensors aren't magic, right? Like an ultrasonic sensor uses sound waves to measure distance. But what if that sound hits a soft, fuzzy sweater that just absorbs it, or an angled wall that bounces the sound completely away? Understanding these quirky physical limitations is exactly what turns a novice builder into a seriously advanced problem solver.
Section 3, Unit 3, Program Control Flow. The brain of the robot.
To truly master those basic movements we established back in Lesson 2, we have to look at how structured program control flow makes a robot's behavior flexible and intelligent. Flexibility is the key word here. We don't want a machine that only knows how to drive in a perfectly empty room. We want a robot that adapts to changing conditions on the fly.
Let's define the tools inside our robot's brain, starting with sequencing. This is just putting instructions in the exact right order. Think of it like baking a cake. You obviously can't put the flour in the oven before you've mixed it with the eggs, right? In robotics, sequencing means making sure your robot turns its sensor on before it tries to look for a wall. Order is literally everything.
Next up, we have loops, which let our robot repeat behaviors automatically.
Say you want a robot to drive in a square. You could write out, move forward, turn right, move forward, turn right, on and on. But imagine how agonizingly tedious writing that out 20 times would be for a 7th grader. Actually, scratch that. It'd be tedious for anyone. Instead, you just write move forward, turn right, once, and drop it inside a loop that tells those steps to repeat 4 times. It saves so much time and keeps the code beautifully clean. Then come conditionals or decisions. This is where the robot uses its sensor data to make choices on the fly, like turning if a wall is in the way. It's your classic if-then statement. If the touch sensor is pressed, then stop moving. If the color sensor sees red, then turn left. This is the exact moment the robot truly starts to feel like it's thinking for itself, dynamically reacting to the real world.
And finally, functions. These let us organize our code into neat, reusable chunks. Imagine you teach your robot a super complicated little routine to do every time it successfully navigates a maze. Instead of rewriting that giant 20-line dance code every single time, you just package it into a function called Victory Dance. Now, whenever you want the robot to celebrate, you just call that one function. It is the ultimate organizational tool for structured programming.
Section 4. Debugging and predicting behavior. Bringing it all together. When you map this all out, it's actually a pretty simple formula. You take the precise sequences and basic movements we learned on day 1, add the environmental awareness of input data from sensors, and wrap the whole shebang in smart decision-making control loops. Put all of that together, and the result is a fully structured, highly capable robot program. Mastering these steps means gaining the ability to accurately predict behavior and debug code. And you know, this entire detective journey traces all the way back to those Unit 1, Lesson 2 guided notes. Because a great robotics student doesn't just guess and check wildly. They look at their code and they can visualize exactly what the physical machine is going to do based on those foundational movement rules. And when it goes wrong, which, let's be real, it absolutely will, they don't get frustrated. They just calmly step back and debug the issue.
I'm going to leave you with this final thought. If sensors always have physical limitations and human code can always be flawed, how will the robots of tomorrow navigate our highly unpredictable real world? The grade 7 students tackling these foundational concepts right now are the exact same people who will be answering that massive question tomorrow, building the self-driving cars and rescue robots of our future. Thanks so much for joining me for this explainer, and keep exploring.